Morning, welcome first of all to everyone. I know that we have our very distinguished guests from many countries on a very short notice, so I thank you everyone. Actually, originally we were thinking to do this seminar only for our class because last time I teach this class on tall buildings, we missed the performance-based design topic. So I told them that okay, after the term, we will do this seminar for the students. And I was thinking that why don't we invite other colleagues also? So we are very glad that people from Brunei, Myanmar, Philippines, and Thailand, and many countries could join us on short notice. And we hope that this topic will be of use to everyone who is involved in the design of buildings. Can you switch off these slides? Here. So basically, what we are planning to do is to, in these 2 days, try to cover the performance-based design in trying to answer a few questions. And the questions are, first of all, the biggest question is, why do we need this? When we have the design code, when everything is there, what is this and why do we need it? Second question is, what is really performance-based design? How can we distinguish it from the conventional design? And then, what is the way to actually do it in practice? So that is why you will see that the program is organized into two grouping of topics. One set of topics are introduction to what it is, how it is done, what is the background, and then the application using the tools. So that's why the application for tall buildings and other buildings using SAP 2000 as well as Perform 3D, we are going to demonstrate. So engineers who are involved in this process can actually use this knowledge or this information to carry out the performance-based design. So let me just, this is an interesting statement. If you look at this one, this is not in your notes. 2 or 3 few slides have been added last minute, but they will be in the notes that we give you in your flash drive at the end of the seminar. So you will get all of the final notes in a flash drive in color because this is black and white and not so interesting. So just bear with me. This is an interesting statement. Long time ago, somebody said that if a builder builds a house for someone and does not construct it properly, and the house which he built falls and it kills its owner, then that builder should be put to death. Right? Luckily, we don't have such strict, clear-cut laws anymore. Otherwise, structural engineers will all leave the job because this is too dangerous. Right? But this gives us something very interesting. Implicit specification, that means properly, should be built properly. What does it mean properly? How do we define what is proper for a house that we are going to build? Second is falls down and kills the owner. That is an explicit performance indicator, right? What is required that it should not fall down and it should not kill the owner. Very, very interesting statement. And then is the consequence. That if it happens, this is what will happen to that one. So long time ago, this was like 1772 BC, this kind of concept of the implicit specifications, performance, and consequence were already built into the codes at that time. But then somehow we forgot these statements and we went another way. Then there is another interesting statement from the Bible, which says, in case you build a new house, you also must put a parapet for your roof, and that you may not place upon the house because somebody might fall from it, right? So just imagine the Bible is talking about these things. What is required here, again, that person should not fall down, but they're not saying how tall the parapet should be. Leave it to the designer to decide how tall the parapet should be so that people do not fall down. But then came the building codes. They say parapet should be 1 meter high. Now problem comes. You build a parapet 1 meter high and still somebody falls down. Who's responsible? The designer or the code which says it should be 1 meter high? Because the designer simply followed the code and now the responsibility is split. It's not clear who is responsible because he can say, the designer can say, I don't know, I was told to build a parapet 1 meter high, I built it. I don't know somebody falls or falls not. That's not my problem, that's not my headache. Because I just follow the code or the specifications. So we come into this issue of the prescriptive definitions against performance-oriented definitions of the thing. If you remember, those of you who are a bit senior, like myself, maybe nobody as senior as mine here, we used to have concrete defined as 1, 2, 4. 1 part cement, 2 part sand, 3, 4 parts aggregate. And that was the specification written everywhere. You should make a concrete which is 1, 2, 4. And that's it. It doesn't matter what the strength is. As long as you put 1 cement, 2 sand, 4 aggregate, you are okay. You are following the specifications. Strength, it doesn't matter. But now, we don't say that. We say, I want a concrete of, let's say, 35 KSC. And I don't care how much cement you put, or you don't put any cement, right? I want that strength. You deliver that strength, and it's your problem. You put additives, you put, whatever you put, it's your problem. So now we have shifted from that simple prescriptive definition to performance-oriented definition. Same thing is now happening or needs to happen in other aspects of the design. That means it's not just, so the design codes simply tell us, do this, do this, do this, and things will be okay, hopefully, quote unquote, hopefully. But will they be? Sometimes they're not, sometimes they are. So we need to go a little bit more beyond this concept, and that brings us to our topic today, which is the performance. So what are the questions that we want to answer? Why do we need performance-based approach? What is this approach? When do we need it? How can we do it? What is the outcome? What are the advantages and disadvantages? So this is what we will try to answer in this session first, an overview. Then we will go into a little bit more details of the nuts and bolts. So first of all, we will see what is the purpose of structural design? Why do we design something? Then second question will be, how do we achieve that purpose? First of all, we define a purpose. This is the purpose of the design. Okay, we know what we are going to, what is the purpose? Second question is, how do we achieve that purpose of the design? What is the mechanism to achieve it? Third is, how to confirm that design purpose has been achieved. It's two different things. I want to achieve the design purpose, this is the procedure to follow, but I have followed the procedure. Has the design purpose been achieved? That is still another question. Then what to do if design purpose is not achieved? Suppose we find that I designed it, but the design purpose is not achieved. What should I do next? What is the consequence if the design purpose cannot be achieved? In some cases, you cannot achieve the purpose of the design, or has not been achieved, or cannot be achieved. What do we do now? What is the consequence of that? So if we look at this way on the design process, then it will tell us that we are lacking a lot of steps in our design process. We only concentrate on how to achieve the design process. We don't worry about we don't explicitly talk about the rest of the issues here. So, what is the purpose of the design? Broadly speaking, main concern is safety, serviceability, durability. We can collectively call performance. Then we also have to see the effects, in this case, effects of winds, earthquake, and so on. And then some effects can be handled without damage. Some effects we may a loss of damage to occur together. You see, it is very hard for laymen to understand that concrete is designed to crack. If you tell them that this beam that you are designing, the building that you're building, is going to crack, they will say, what are you talking about? I'm paying you money. It should not crack. But we start our theory with the assumption that concrete is going to crack. And it's very hard to communicate that to the owner. So some damage is expected, somehow. How much? How to control it? That is the key. That is the challenge. So role of the design codes has been to basically tell us in such a way that that damage, that is within certain acceptable limits. What are those limits? Everything is implicit. Nothing is really explicit. So the design code's role is to guide the engineers, to relieve them of the responsibility, to help the people to check, to be a bridge between the public and the engineers and the designers. So for the most normal cases, the design code will tell us what should be done. But they will not explicitly tell us that what will be achieved if you do this one. I will give you some more specific examples. So conforming to codes gives us what? It gives us code compliance. That's it. Nothing more. So if you follow the code, you basically follow the code. That's what you can say. But you cannot say anything more about the structure, performance, building, or anything. So if you want to say, I have followed the code, that's good. You followed the code, then what? So what? Public doesn't really care about the code is followed or not followed. They want the structure to be performing well or economical and so on. Performance is not guaranteed automatically by code conformance. That is very important for us to recognize, that code conformance does not automatically mean performance. Performance can be achieved without code conformance. Two statements are very important. You may follow the code, still not get the performance. You may not follow the code, may still get the performance. Look at the pyramids. They weren't built before any code was developed. They had very good performance, no problem. All the 7 wonders were built before the codes were developed. They had lived up to the times. So that means good performance is not code dependent on code compliance. And code compliance may not necessarily lead to good performance. So these 2 or 3 things we need to sort of distinguish. So if you go that way, then we can say for new structures, what can the performance-based design do for us, or how can it help us to think about this one? And we can say this basically attempts to check or evaluate the performance once the basic design objectives have been set and design is done. So when the design is carried out by the code, then performance-based design can help us to verify whether the design objectives have been achieved or not. That's the role of performance-based design for new design. Provides means to study and use alternatives. It gives you the opportunity to deviate from the code. For example, the most common example is when you're building a tall building, one of the requirements in most of the codes is that if the building is taller than, let's say, 160 feet or some round number like that, then you must have a shear wall and a frame work together, where frame should carry 25%, shear wall should carry 75%, so on and so forth. It's practically impossible to achieve that in a tall building. Why? Because frames are very few. It's a small building, is very tall, only a few columns, mostly scored wall. A few columns cannot take 25% of the lateral load. You cannot force them to do that. They normally take 4, 5, 6%. If you enforce 25% criteria, your structure will become impractically expensive. That is when performance-based design can come in and say, okay, let me check whatever you have designed, is it okay or not? I don't care about this 25%, 75% thing, because that's just arbitrary. So those are the places where the performance-based design can come in and help us to go beyond the code or deviate from the code or study alternatives. And as long as we can prove their work, they are acceptable. Complement the conventional design by providing greater insight into the design. We will see that performance-based design is 2 or 3 levels more sophisticated or difficult or advanced than code-based design. So that means it will help us to understand the structure better. So it will help us to understand the structure better so we can come back and improve our code-based design. So in any case, performance-based design is going to help us in the new design at many levels. For existing buildings, okay, for new buildings, this is what we can do. What if the building has already been constructed? That is where the strength of the performance-based design really comes in. Because you cannot make an existing building conform to the code which is now in place. It's just not practical. The codes are designed to follow the procedure to design new buildings. Once they're already done, you cannot now ask the code, the building to conform to a new code. By definition, the codes are wrong. The code that you have today, by definition, is wrong because it will be superseded by a code in 2 years. So that means, by definition, the current provisions are not right because they will be proven wrong in just 2 or 3 years, because that has been happening for the last 100 years. Every few years, new versions of the code comes in, new methods come in, new things come in, and which say, oh, what you did last 2-3 years ago, no longer correct, right? So you cannot say that the buildings that I built 30 years ago, now every building must follow the new code. Impossible. Codes keep changing every 2 years. You cannot keep retrofitting the buildings every 2 years. So clearly, code conformance is not practically possible for existing buildings. Another problem is that now we have international environment. Designers from all over the world work all over the world. So let's say a designer comes into Thailand and he designs the building based on Eurocode. Another designer comes, designs the building on is American code. Another one uses Thai code. They're all permitted within a certain limit. According to one code, the same building, exactly the same building is acceptable. Another building is not. Another code is not acceptable. Question is the building acceptable or not acceptable? It can either be yes or no. It cannot be code dependent because building is either safe or not safe. It's not a code dependent question. So which means that the code conformance for existing building is not the way to evaluate their acceptance. We need methods better than that. And that method normally is now performance-based design. And this basically checks the effectiveness of the retrofit techniques. So if you, first of all, you evaluate it's okay or not. Performance is okay or not. We don't care whether it followed the code or not. And I will tell you later why not. Then if it didn't follow the code, how to fix it? And will the fix work finally? Those are the questions that the performance-based design can answer for us. So it provides a means for existing structures to meet the design objectives, new or original, without the need to conform to a specific version of the code. And that is where the performance-based design comes in handy. So what are the performance objectives that we are talking about? Basically, these are KPI. Those people, engineers are not, civil engineers are not used to the term KPI that much. But every other engineer, every other discipline, every contract that you have has KPIs in it, key performance indicators. I remember when we were finalizing the contract for AIT for this infrastructure management, the main thing that was discussed was KPI. What do we expect the contractor to do? We are not asking him to clean the windows we can ask him to clean the windows every other day. And still the window may not be clean. So if he cleans it, it doesn't matter. But we say if the window has to be clean and clear, it doesn't matter how many times it's clean, then KPI is what we target. We don't target the provisions. And KPIs can be always agreed between the person who is writing the paying for something and the person who is doing the job. They can both sit down and agree, this is the key performance indicator that we agree, and this is the corresponding cost for these performance indicators. So the owner or the client can sit down together with the PPD consultant or designer and say, this is what I want from this building. But because public is involved, public safety is involved, these two parties are not enough. Because they may decide on something which is not in the interest of the public. So we have two more parties involved there. The one is called independent reviewer, always required. If you're doing performance-based design, we also need an independent reviewer, a third party, who can say that, okay, whatever you people are saying, it makes sense. Because you cannot agree on something which will endanger the public safety. Then the fourth one is the guidelines which the community have developed at large. So we have the designer who has some knowledge, we have the independent reviewer who is supposed to be an expert in this area, and we have the whole community of engineers at large who have agreed on certain things to do. So the international guidelines are those guidelines which the community has agreed, engineering community has agreed, not in engineering, insurance people, public officials, engineers, academics, everybody has agreed that, okay, this is the way to go. So these four parties come together and they decide what the key performance indicators will be. And based on that, then we can carry out the entire design. And they can be changed. These are not written in stone, as they say. So international guidelines are not codes. So they do not have any legal binding. You are not obliged to follow them. They are guidelines preferred to be followed. So let's talk about earthquake. Of course, PPT can be used for any type of loading and structure, but mostly we use it for earthquakes. And the reason will be clear soon enough. And if you look at the world map, these are the areas where you have a lot of high seismicity. So these people in Africa probably do not need to attend this topic, so we don't have anybody from Africa anywhere, right? Because no earthquake. Some parts of Europe, Russia, Australia, so they are safe. Most parts of America, they are okay. But we are in a region, most of our countries are in a region where it's not okay. We are in a, this region is not quite active. So earthquakes become significant concern for the designers. And this is what may happen during an earthquake. You can see the entire city is flattened, not a single building left standing. This is in Pakistan for a few years ago. 80,000 people died, the whole city completely flattened. And we have seen similar things happening in many countries, in many earthquakes. So here also you can see some more buildings collapsing, Haiti, other buildings in different countries. So we know that earthquakes actually do cause failures and damage and deaths. So that means something needs to be done to stop this from happening. Interesting, the whole building is, one floor is gone, the rest of the building is still standing. So we can see that there are many issues with the earthquake design. And the second issue is responsibility. Who is responsible if that happens? If the building has collapsed in an earthquake, whose responsibility was that? So many parties involved. Client, owner, architect, structural designer, geotech consultant, peer reviewer, builder, contractor, building officials, legal system, structural design codes, and so many things. So many parties are there. Now, after the earthquake collapse, who is responsible for this? Very difficult to assess. But in reality, ultimately, it should be these people here. Because they are the ones who are professionals. They are engaged to do this one. The other people are just around them, relying on them. So ultimately it comes to us to make sure that it doesn't happen. So public concern is simple. Their questions are very simple. I think all engineers at one time in their life have been asked this question. Is my building safe? Can you give me a certificate that the building will not fall down? What do you do? Did you ever give that certificate, Mr. Anand? Never. You ask me, I will also not give. We have a problem and we have a project in Bangladesh right now, and the client is asking us, please certify that building will not fall down in an earthquake. I said, no, we are not going to certify that even if you give us $1 million, because this is something that we can't do in the current system unless we do a certain advanced analysis. But we should be able to do that, because when you buy a product, a phone, it doesn't work. You go back to the case, it's a 1 year warranty, change my phone. Building falls down, structural engineer doesn't give the building back. It has no warranty, right? So we are the only profession left which has no warranty. We want warranty for everything except structures and software. Also, we don't have any warranty. So software doesn't work, you cannot do anything. It's just written there in the disclaimer. Anyway, so the owner wants to know, the building public wants to know, will the building be safe? The owner wants to know, will the building collapse? Will it be damaged? If it will be damaged, can I repair it after the damage? How much will it cost to repair it? Right? So these are the questions from the owner. How long will it take to repair it? Can I make building that will not be damaged? Right? He has a valid question. He can say, yeah, I'm willing to pay the money. I don't want to damage building later. Can you make a building which will not be damaged? So if you say I will follow the code, you cannot guarantee that. But performance-based design can help us to do that, to make that statement. Public officials, who is responsible if the life of loss occurs? So everybody has their own concern. So we need to bring all of these people together, and that is where the performance-based design can become useful. Structural engineers, our dilemma is that we cannot answer most of these questions explicitly. Answers are always qualified. If you ask me, building will collapse, I say, yeah, but which loading? If the construction is done properly, and this one, and this one, and this one, yeah, it will not collapse. So we have many steps before we can make that statement. There is no warranty for the structure. There are too many unknowns. Public understanding and engineer understanding of safety is different. The designer ultimately has to hide behind the design codes. He says, I follow the code, so they strictly try to follow the code to save themselves. They don't care about the building. They care about themselves, so they follow the code, so no one can touch them. But their real concern is not the building, it's themselves. But performance-based design, the concern is the building, not us, right? So seismic demands are different. This actually is very good. Performance-based design provides a means to link the hazard levels to the performance levels. Now we are getting a little bit technical. We have done enough general stuff. Let's get a bit more specific. So now we are saying that PBD provides a means to link the hazard levels with performance levels. I will explain what does it mean. Various hazard levels can be linked to various performance levels. That means we can say for this hazard level, I may have this level, this performance, or this performance. And for this one, I may have this one. So we have a multiple choice on both sides, and we can mix and match. Allow the purpose of the design and the effectiveness of the design to be related and evaluated properly. So basically, performance-based design will allow us to link the design objective with the effectiveness of the design and the achievement of the design. Help to check and improve the performance so the building do not collapse, are not damaged extensively, and public life safety is ensured. So ultimately, we focus on this one. So we can now more explicitly say, okay, I'm going to design a building which will not collapse under this earthquake level and will not hurt people. So we have already talked about that implicit performance objectives are not enough. That is what the codes assume. They say if you follow the code, the building is expected to be okay. A general building is expected to be okay. They say nothing about this particular building. Because we have found in the past that if you follow the code, generally speaking, the buildings should be okay. But every building is unique. Every site is unique. So this does not really cover everything. And they're explicit for earthquakes. They say that resist the design level of earthquakes with damage without causing loss of life, resist strongest earthquake with substantial damage with very low probability of collapse. This is the intention of the code. But what is exactly happening here in these three statements? So we basically, if I summarize, three things. Earthquakes that come often, building should be perfectly fine, no problem. Earthquakes that come rarely, the building should be maybe damaged but should not collapse, nobody should be hurt. And earthquakes that come maybe extremely rarely, once in a long time, still the building should not completely collapse. It may damage extensively and may not be repairable, but still it must not fall down and kill the people. So that is the intention of the codes. But the intention is not clear in the provisions. It cannot be verified that this has been achieved. Performance-based design gives us the opportunity to do this very explicitly. So, performance-based design code approach is specified. Let's say we take the interesting example of a beam and stirrup tie spacing. At the end of the beam, the codes say that you should provide for earthquake-resistant design a tie spacing of not more than 100 millimeter. First of all, where did this come from? Why not 105? Why not 95? Because 100 is a ground good number. In inches, it is 4 inches, 1/3 of the foot. Anything else would be not round, so 4 is chosen.